Hey y'all, we are Memphis Community University and we're back for another Calculus Done Wrong lesson where we wrong calculus before calculus wrongs us. And today what we're going to do is we're going to conclude our BC integral method playlist. What we're going to do is we're going to review all those integral methods that we learned previously. So nothing new today, just a big comprehensive review. So keep in mind that of course BC includes the AB topics as well. So what we're going to try to review is all these topics that I'm about to list. We're going to do basic integrals that don't require any special integration method. We're going to do U-subs, indefinite, definite, and general. We're going to do integration by parts, again, indefinite, definite, and general. We're going to do partial fractions, indefinite, indefinite. And also we are going to be doing improper integrals at some point throughout this video. So what we would highly encourage you to do, if you don't know how to do one of these integral methods, is to watch our previous video in our playlist. We have videos for every single one of the integral methods that I just described and that we're going to be practicing with throughout this video. And what we would encourage you to do is to watch that video, know how to do each one pretty well, and then come back to this one and just see if you can sort of carry out doing every single integral that could potentially be on the AP exam. The hard part about this, of course, is that each one isn't hard in general, but the hard part comes when you mix them all together. So if I say this is an integration by parts question, you're just going to do the process of minus dub, you're going to do liate, all of that sort of stuff, and you're just going to carry out the process. Same thing with a U-sub. Here's a U-sub. Try to do this U-sub. The hard part is when they mix it all together and you have to determine, should I do U-subs and should I do parts, should I do partial fractions? So that's what we're going to try to focus on in this video. What we're going to try to answer is, before we start the question, is how do I do this integral? What's the best way to do this integral? And then once we do that, it should be pretty good. We'll just follow the steps and we'll be good to go. So let's do a lot of integrals today. It's going to be a quite long video. We're doing BC integrals. Don't want a really big heading because I'm going to write a lot of stuff on this board and the board isn't very big. But let's do a lot of BC integrals today. So first off, I'm going to do 3 separate integrals. Again, what we're trying to do is compare the difference between them. My first integral is going to be this. We'll put some numbers here. This will be our only improper integral. So let's start off with an improper integral. We'll go x squared plus 1 over x cubed as my first question. Let's see, that should be good enough. Then we're going to do the integral of, let's say, 2 to 3 of x squared plus 1 over 2x. And then we'll try to do this integral, which is going to be somewhat similar. It's going to be x minus 1 times x plus 3, 2x minus 1, maybe 2x minus 4, 5 or something. Change it up a little bit. And then we're going to have numbers. Let's have the numbers 3 to 7. So 3 separate integrals. If you want, pause the video a little bit and practice them. Certainly always best to practice your integrals. You're going to get better at integrals just like with derivatives if you just do a bunch of integrals over and over and over again. So I highly encourage you to practice each one of these. Pause the video, at least ask the question, how do I do this integral? And in 10 seconds, 10, 9, 8, 7, 6, 5, 4, 3, 2, 1, I'm going to talk about them. Let's talk about them. So hopefully you had a good chance to try to practice the integrals for yourself, but let's do this one. So this case, it is an improper integral, so you do have to do the b thing. You have to write the limit as b goes to infinity, and then we're going to write the integral again. So on the AP exam, or in college calculus exams, it's sort of improper to write infinity on the top, so that's why we write it with a limit. So this is a famous integral, so keep in mind that, again, the main choice we're trying to do is trying to determine what kind of integral method that we're trying to do here. So this is a famous one where you don't do any integration method. It's really algebra. I call this the split numerator. So this is the split numerator, this first one. You're allowed to split numerators to make it easier, 2 easier integrals, but you cannot split denominators. So we're probably not going to use this strategy for this one right here. So in this case, when you split the numerator, it's going to be x squared over x cubed plus 1 over x squared. And we still have dx here. Let me try to erase this line and put a dx. Hopefully I'm not writing too small, but we need a lot of space for this guy right here. So remember that when you split the numerator, you still have to do the integral correctly. So what that entails is that we have to simplify each of these 2 terms. So I'm going to do that real quick. Again, I need to write a little bit small. So it's the limit as b goes to infinity, the integral of 2 to b. and then x squared over x cubed is 1 over x. Again, the point of split the numerator is to split it into two separate questions. I'm going to write the next fraction as x to the minus 2. I'm not doing this for 1 over x because of a very specific reason, but anything that's not 1 over a linear term, but this is 1 over a quadratic, I like to write as a power because I'm about to do the power rule. So in this case, what we're going to do is we are going to take the integral. Let me try to erase this line completely. So what's the integral of 1 over x? The reason why I didn't write it as a power is that because it's ln. So we're going to write limit as b goes to infinity, and then we're going to, the integral of 1 over x is ln of x. Then the integral of x to the negative 2. Again, we are using the power rule here. So you take the negative 2, you add 1, and then you flip. So in this case, it's going to be minus x to the minus 1. And then we're going to plug in, again, b and 2. So this is the fundamental theorem of calculus. Every single time when you have numbers, no matter what the antiderivative method that you choose, you have to do the fundamental theorem of calculus, plugging in the top minus the bottom. So in this case, what's going to happen is something weird. We're going to get ln of infinity. Then we're going to get 1 over infinity. Plugging in 2 is a lot more normal. We're going to get ln of 2 minus 1/2. So let's just try to finish this question. And then once we finish this question, perhaps we'll just erase the work so we'll have enough space to do this one. But if you don't know, ln of infinity is infinity. 1 over infinity is 0 because you have one thing and you're splitting it up amongst an infinite number of things. All these are normal constants, so it's minus ln of 2 plus 1/2. But it looks like if you have infinity minus ln of 2 plus 1/2, you're just going to get infinity. So this integral diverges, meaning that it doesn't go to an answer, a finite number, but that's okay. That's certainly a valid answer in and of itself, and this is the answer. So again, this was a nice little split numerator where we had an improper integral and we wanted to practice improper integrals. We first did the improper integral process, which is write it as a limit for some reason. I don't know why they want us to write it as limits, but I don't really question my authority. So I write it as limits, limit as b to infinity. I did split up the numerator. It is not a u sub. Even if this derivative sort of looks like this, you can split up numerator, so you might as well do that. So I split up the numerator. When you split up the numerator, you do have to simplify before you take the antiderivative. But once you take the antiderivative, it doesn't require any sort of u sub process. So you just do top minus bottom, and then you're good to go. In this case, we got infinity. Sometimes when you have improper integrals, you're going to have infinity, perfectly valid answers. Sometimes you're going to have finite numbers, also perfectly valid answers. So that's the answer to that one. Hopefully you've written this down. If you didn't write this down, remember that technology is magical. You can just pause the video and write it all down. But I do want to erase this work so that we can do this integral right here. So hopefully my work isn't too crazy today because we're doing multiple integrals every single time throughout this video. We're going to do rounds and pairs of integrals. Hopefully my work isn't as unorganized as usual, but it could be more unorganized as usual. So let's see what happens. So we're going to erase that first integral and we're going to do this second integral, but let's put it on the top here. So this is going to be the integral of x cubed plus 1 over 2x times dx. So hopefully you can recognize that this one is a u sub. Why is this a u sub? Again, what we want to be asking ourselves is this integration by u subs or is this integration by partial fractions, the ones that have fractions? Well, remember on the AP exam, partial fractions has to be factorable in the bottom and quadratic. Well, x squared plus 1 is not factorable, so it cannot be partial fractions. It is a u sub because the u is x squared plus 1 because its derivative is in the question perfectly, actually. But even if it was just an x, it would still be a u sub. So in this case, it's going to be u is equal to x squared plus 1. It's going to be du is equal to 2x times dx. And then we are going to change all of our x's to u's, as we like to do in our u subs. So we're going to write an integral. I chose this u so that I can put it on the bottom here. So it's going to be divided by u. Then I will look for my remaining x's. Looks like it's x and dx. So I'm going to solve for that. It's going to be x times dx is equal to du over 2. So instead of the x and dx, I want to replace those x's with u's. So that becomes du over 2. I'm going to write du over 2. But just like normal, I like to take out my constant. One of my favorite hobbies in life, taking out constants of integrals. So we're going to take it on 1/2. But again, this was d over 2. We took out a 1/2. This is going to be 1 now. There is a 2 here, and again, I'm going to employ my favorite hobby. I'm an expert in it by now. I'm going to take out that constant out, so that 2 also gets taken out, so that's going to be 2, so obviously these will cancel. The key that you have to remember that some students forget is that you have to change the x numbers to u numbers. So how do you do that? Well, what you're going to do is you're going to take your x number and just plug it into the function. So our old bottom number was 2, that was the old x. What we're going to do is we're going to plug it into u, so 2 squared plus 1 is equal to 5. So that means that our new bottom number is going to be 5. Same thing with the top number. This top old x was 3, we're going to plug it in. 3 squared plus 1 is going to be 9 plus 1, that's going to be 10. So again, old x, old y, we plug it, old x, old top, old bottom. And what we do is we plug it into u to find a new top, new bottom for u numbers. Then, once you change everything to u's, another thing to remember is that you can forget about all the work that came before it. We can make a nice little dividing line. Everything is u's, including the numbers. So what we're going to do is we're going to take the antiderivative with respect to u, and we're not going to plug in x squared plus 1, we're not going to plug in 2, we're not going to plug in 3, because we changed everything to u's. U's are important, x's are no longer important, let's just remember u's. So what we do is we get this easier integral, it's going to be ln again. And what we're going to do is we're going to plug in 10 and 5. That's going to be ln of 10 minus ln of 5. If you're feeling a little frisky, you'll know that the subtraction of ln's is actually the division of a single ln. So this is going to be the same thing as ln of 10 divided by 5, but I'm just going to write it as ln of 2. So that's a very classic example of a u sub, and it's pretty obvious that it's a u sub because you can't do partial fractions because the denominator is not factorable, and the derivative of the denominator is the numerator. That often happens when you have fractions where the derivative of the denominator is the numerator, not the other way around. If it was the other way around, it would probably be a split numerator. But this is our normal u sub process. We choose a u, we change all the x's to u's, including the numbers. And how do you change the numbers? You plug in your old numbers into your u. So this guy on the right here, this is going to be our partial fraction guy because we have something that's factored. If it wasn't factored, we would have to factor it. And then we have a numerator that's linear. So this is your partial fraction thing. Again, it potentially could be u subs where the u is the bottom, but if you take the derivative of the bottom, you're not going to get a multiple of the top. So this is a partial fraction example. And I like partial fractions because you just do the same thing every single time, even if it's a pretty long process. So let's do it. Again, what you do is you break it up into each of the factors. And what you're trying to do is you're trying to find a and b so that this partial fraction decomposition works. We do have numbers on the integral, but that's actually not that bad. We're just going to take the antiderivative at the very end and then plug in top minus bottom. So let's just do this real quick. What you do is you cross multiply. So in this case, what we're going to get is a times x plus 3 plus b times x minus 1. And we set it equal to the original numerator. Keep in mind that sometimes the numerator is just a single number, that's fine. Sometimes it's just an x, that's fine. Sometimes it's just dx. And if the original numerator is just dx, keep in mind that is equal to 1. But in this case, it's pretty obvious. It's 2x minus 5. Let me see if I can squeeze a little minus 5 in there. It looks like I can. Then what you want to do is distribute. Some people don't do this step, but I think this is a useful step. So we're going to distribute. And then using this equation, we're going to form two new equations. One is going to involve x's, one is not going to involve x's. So it looks like our first equation is going to be ax plus bx is equal to 2, which means that a plus b is equal to 2. Then my second equation, is my not x equation. It's going to be 3a minus b is equal to negative 5. Minus b is equal to negative 5. So it looks like I have my system of equations. And now I just need to solve my system of equations. Looks like the easiest way will be to eliminate, add these two equations together. You'll eliminate the b. I think you're going to get 4a is equal to negative 3. Because you're going to get a plus 3a is 4a, b minus b is 0. That's why we eliminated. 2 plus negative 5 is negative 3. So it looks like our a is going to be negative 3/4. So that means our b is going to be, well, if a is negative 3/4, we're going to add it to the other side. 2 is 8/4, so it looks like our b is going to be 3/4 plus 8/4, which is 11/4. So now we're good to go. Now we end the algebra and we're back to calculus. What we're going to do is we're going to take our integral and we're going to replace it with negative 3/4 for the a, and we're going to replace it with 11/4 to the b. But I like to also do a second step. Again, I like to have the habit of just taking my constants always outside of the integral. So what I'm going to write is I'm going to write the integral from 3 to 7. Instead of putting the a on the top, I'm just going to write negative 3/4 out here. It's going to be 1 over x minus 1. Then we're going to add the integral. Again, I'm taking out my constant, so I take my little hand, I put the 11/4 where the b goes, but I take it out of the constant, just push it aside. So it's going to be 11/4 then, integral of 3 to 7 of 1 over x plus 3. Then you can have dx's. Try to not forget your dx's like I always do. So now the time is to take the antiderivative. Keep in mind that for these integration by partial fraction questions, once you get to this step, it's always ln for the antiderivative. On an AP exam, on a college calculus exam, it does get a little bit trickier, but on an AP exam, it will always be linear, so it's always ln, but it's not always perfectly ln. It could be ln times a constant. So for example, if we had something like 1 over 2x minus 1, that antiderivative would be ln of 2x minus 1 times 1/2, because you have to multiply by the reciprocal of the derivative of the inside function. We'll talk about that a little bit in future questions. But for here, because the derivative of both of these guys is 1, it's just going to be normal ln. So in this case, the answer is negative 3/4 ln of x minus 1. And then it's fundamental theorem of calculus after we take the antiderivative. So it's going to be 11/4 ln of x plus 3. But keep in mind, again, that sometimes it's not ln of the thing. If this were switched like 1 minus x, we would have to change this to a plus because we're skipping u subs in our head. So at the end, of course, you do have to plug in 7 and 3 using the fundamental theorem of calculus. Let's just plug it in real quick and let's not simplify anything because that's not really the point of the video. So it looks like you're going to get negative 3/4. We're going to write the answer in this little box right here. Negative 3/4 times ln of 6. Keep in mind that there's a lot of minuses when you're doing integrals in general because there might be minuses from u subs or du, dv when you're doing integration by parts. There's minuses when you do top minus bottom when you're applying the fundamental theorem of calculus. So just be careful. In this case, when we plug in 3, it's going to be ln of 3 minus 1, which is the ln of 2. But it's going to be minus minus because there's already a minus and it's top minus bottom when you evaluate. So it's going to be plus 3/4 ln of 2. You could simplify this again using that division rule, but I'm feeling a little bit lazy. I want to finish the question. So it looks like when we plug this in, you're going to get 11/4. Still plugging in 7. I'm doing top minus bottom twice. I don't know why I'm doing that. Let's erase this. Let's plug in 7 into all of this first. So it's going to be 11/4 ln of 10. And now let's plug in 3. So when I plug in 3, it's going to be minus. When you plug in 3, it's going to be negative 3/4. So that's why it did become plus. You could have done top minus bottom into this, top and minus bottom into this, but we might as well just do top minus bottom one time. So we're going to plug in 3, so it's going to be negative 3/4 ln of 2, and then it's going to be 11/4 ln of 6. And again, you can simplify this, of course, especially these ln of 6's, but I don't want to do that because I want to focus on the calculus. So this is integration by partial fractions. Again, I did a little bit of a weird thing in top minus bottom, but hopefully you understand the process. You recognize that it's integration by partial fractions because you determine it's not a u sub because the denominator's derivative is not the numerator or a multiple of the numerator. So what you do is you break it up, you cross multiply as we did, then you start distributing stuff. Then you form two equations, the x equation and the not x equation. The x equation in this case was ax plus bx is equal to 2x, so it's this thing right here. The not x equation is 3a minus b is equal to negative 5. We solved this simple system of equations using elimination. Then we took our a and b and placed them in the right spots. Here's a, here's b. We took them out because we'd like to take out integrals. Then when we take the antiderivative, it's always ln, perhaps times a constant in the front. In this case, there was no constant, so all we did was we did top minus bottom, plug in 7, then we plugged in 3. There was some simplification that you could have done further, but this is a valid answer, so we're going to leave it like this. So again, once you recognize that this was partial fractions, the process wasn't that bad. Once you recognize that this was u subs, the process wasn't bad. We just had to go through the question. Let's do a few more. Actually, not a few more. Let's do several more, just so we can get the idea of when to do what. So usually people don't confuse partial fractions with integration by parts because they look so different. So really the main question you're asking is, do I want to u sub or do I not want to u sub? For the left question, we u sub. For the right question, we did partial fraction. So let's try to explore that idea again. So let's say we have the integral of ln of x, let's say it's cubed, I don't know, of x, and we're going to plug in the numbers, let's say e squared and 1. Then we are going to do the integral of just plain ln of x dx from 1 to e squared as well. So try these two integrals. Again, what you want to do is ask yourself how to do these integrals, and the main question you're asking yourself in order to answer that other main question of what to ask yourself is, do I u sub? So ask yourself, do I u sub for each of these? And then if I don't u sub, what should I do instead? So I'll give you 3 seconds. I won't watch you work. 3, 2, 1, let's get going. So hopefully you recognize, even though this doesn't have a dx, that this is the u sub and this is not the u sub. And how do I know that? Well, I have ln of x. That's the most likely case for a u choice. And notice that the derivative of ln of x is in this question. What's the derivative of ln of x? Well, that's 1 over x. So I'm going to start the question. Looks like it's going to be u is equal to ln of x, then du is equal to 1 over x dx. Once you start doing the u sub process, it should make sense. If you get stuck somewhere, don't worry. It's either because you chose the wrong u or the question you're not doing is a u sub. So just take your pencil or your marker or whatever, erase your work, just start over with a new first step. But if you're doing the question correctly, everything works out pretty nicely. So for example, in this case, when we let u be ln of x, that immediately makes our u be placed right here. Why we chose ln of x is that we can replace it with the u. We got u cubed. Then we look for our remaining x's. Looks like it's dx and divided by x. That's exactly this line. So instead of writing dx over x, I'm going to substitute in du times du. Then I do have to change the numbers. Keep in mind that that is a process that some students forget. So what we do is we take our old bottom number and top number. So when x is equal to 1, what we're going to do is we're going to plug it into the function, but that means u is equal to 0. That's a common ln that you should know that it appears quite often. Ln of 1 is 0 because e to the 0 is 1. So in this case, that is going to be 0. Then we have this other e squared number, so x is equal to e squared. We have to plug that into ln, but if you don't know, ln and e are inverses, so ln of e to any power is that power. So that means our new u number is just going to be the nice number 2. So we have 2 here. Again, just remember that we change all of our x's to u's, so we can forget about x's for the rest of the question. Above this line, I don't have to think about it all. I don't like x's, I like u's more. Notice that my integral is very simple and I change all the x's to u's, including the numbers, so I can just go for this u integral. So what's that going to be? Well, what's the integral of u cubed? It is the power. We'll take that old power, add 1 to it, so it's going to be u to the 4th. Then we're going to divide by that new exponent, which is divide by 4. That's the power rule. Then we're going to plug in 2 and 0. Fundamental theorem of calculus time. Again, I did not plug in e squared to 1. I did not plug in ln x. I just kept with my u numbers. So it's going to be 2 to the 4th over 4 minus 0 to the 4th over 4. After the fundamental theorem of calculus, plugging in the top minus the bottom. And in this case, what is that? Well, 2 to the 4th is 16. So it looks like it's going to be 4 minus 0. 0 to any number, just the best thing in the world. Just 0. Looks like my answer is just 4 here. So again, nothing too crazy. A pretty standard u sub where I changed everything to u's, including the numbers. This one is on the right here is not going to be a u sub because if you let u be ln of x, you won't have any dx over x to help you sub in. This is an integration by parts question, and it's nice to recognize that it's famous that ln of x is done by integration by parts. The integral of ln of x, the integral of inverse sine of x, and the integral of inverse tangent of x are all done by integration by parts. So remember that with parts, we have these two things. We first have the phrase liate, which helps us determine between u's and dv's when we start doing the integration by parts process. What happens is that letters that are on the left side are going to be your u because they have easy derivatives and hard integrals. And then letters on the right are going to be your dv because they have easier integrals. Remember that this phrase, liate, L stands for logarithms, including ln of x, so this is going to be an L. I stands for inverse trig only, like inverse sine or inverse tangent. A stands for algebraic expressions like x squared plus 3 or x plus 2, or even just dx itself. Really, it's 1 times dx, where 1 is algebraic. T stands for trig, like sine and cosine, not inverse trig, because that was I. And then E is exponential, like e to the x, something to the x, 3 to the x, 2 to the x, things like that. So in this case, we have L and A. Then we start forming this rectangle, U, du, V, dv. Because L is to the left of A, that means ln of x is going to be a good choice for U, and that means dx has to be my dv. I like to draw arrows here because I have to take the derivative of U, and then I have to take the integral of dv to finish the question. What's the derivative of ln of x? Well, that's just 1 over x times dx. And then what's the integral of 1 times dx? So easy that it's hard, but what's the integral of 1? Well, the integral of 7 is 7x, because the derivative of 7x is 7. So the integral of dx is just x. So then you employ this formula right here, u times v minus the integral of v times du. Still going to plug in these numbers, 1 and e squared. So let's write this form. In this case, what it's going to be is ln of x times x, u times v. So we're going to put the x in the front just to make it look a little bit nicer. Then it's going to be minus the integral, still with the same numbers. So we forgot the vertical bar, 1 and e squared. This is going to be x. So notice that there's no changing of the numbers like u subs. It's just always going to be x numbers because we never write anything beyond x's when we actually are writing the integral. Then we're going to do u times v, so that's the uv, minus the integral of v du. What we're going to do is we're going to do top minus bottom just like the other one. So we're going to first do top minus bottom and just to the uv part, and then we'll deal with this integral later. I like to do that when I do integration by parts definite. So we're going to plug in e squared. It looks like we're going to get e squared times ln of e squared. But remember, ln of e squared is 2 because ln of e to any power is that power. So we're going to have 2 here minus 1 because we're plugging in 1 times ln of 0. But ln of 1, sorry, ln of 1 because we're plugging in 1. Top minus bottom. Ln of 1 is 0 though, so it goes away. And then we have to do this integral right here. So that was the top minus bottom of just the of part. Now I need to do this integral. Unfortunately, the integration by parts doesn't spit out the answer immediately. What you have to do is you have to get an easier integral, but there's various ways to do this easier integral. So in this case, the easier integral, the best way to do it is what you're going to do is you're going to cross out these guys. So you're just going to have the integral of 1 over e squared, and you're just going to have the integral 1. Again, you do have to do the second integral. It could be another u subs if you're unfortunate. It could be partial, another integration by parts. That's the worst case scenario. But in this case, it's not going to be too bad after you simplify because the integral of 1 is just x. So now we have just e squared times 2 from the uv part. Then we have minus x. And we're just going to plug in e squared and 1. And to just this part right here, keep in mind, we're not plugging into this part because this was outside the integral. So this is e squared and 1. So it looks like our final answer is going to be 2e squared. And then we have minus. And then we're going to do top minus bottom, so it's going to be e squared minus 1. So our final answer looks like we're going to subtract 1e squared from 2e squared. So it looks like our final answer is going to be e squared minus 1 plus 1. Again, be very, very careful with those negatives, but hopefully you see that this is a pretty standard integration by parts question. It is the opposite of the product rule, so you have to determine what are the two products. In this case, it's ln and dx. U was ln of x. dv was dx because Leote told me so. Things on the left are u's, things on the right are dv's. Then you always take the derivative, you always take the integral, then you form the function uv minus the integral of v du, perfectly right here. Then you do top minus bottom into the uv part, just like this. Then you have the second integral to deal with, but you first simplify it if you need to, and then just take the antiderivative however you need. The question demands, whether that be, in this case, just a simple power rule question or a u sub question or an integration by parts question. So that's that. Let's do a few more rounds of this, parts versus u subs, because again, that's the hardest choice. So I'm going to erase this. Sort of getting, my mouth is becoming dry a little bit. I need some water, but I'm going to try to power through. Let's try to do as many examples as possible. So in this case, what are we going to do? Let's do the integral of x times sine of x squared, and then we'll do the integral of x times sine of 2x. So again, two questions that look very, very similar. Pause your video, try them out for yourself, and just determine, do I u sub this or do I not u sub this? And if I don't u sub this, it's probably parts. So 3, 2, 1, let's get going. So in my opinion, this is going to be the u sub, because notice that the derivative of this guy is a multiple of something that's in the question, where the derivative of 2x is not a multiple of x. So in this case, this is going to be the u sub. Let's go through this u sub fairly quickly because it's not that bad. U is equal to x squared, du is equal to 2x times dx. So we're going to change all of our x's to u's, and we have an indefinite integral, so we don't have to worry about the numbers. We chose this u so that we can place it right here, sine of u. Then we are going to take the, replace these remaining x's. These are going to be my remaining x's, so I'm going to use this line to isolate my remaining x's. Looks like it's going to be du over 2, so we're going to write du. We could write divided by 2, but oftentimes it's easier just to bring out the constants, so that's what we're going to do. We did our mission, we changed all of the x's to u's, so now it's time for the antiderivative. Remember that the antiderivative of sine is negative cosine, so it's going to be negative 1/2 cosine of u. We're going to add c, and then at the very end, if you have an indefinite integral, unlike a definite integral where we change all the numbers, you do want to plug back in this x, so it's going to be negative 1/2 cosine of x squared. Pretty standard u sub. You want to see this level of question. This is going to be integration by parts because you have two things that are unrelated to each other in terms of derivative. Slightly harder question. So again, using Liate, this is going to be a algebraic, x is algebraic, like x squared plus 1 or x minus 2. This, of course, is trig because it's sine or cosine. So it's going to be u du, v dv. So because a is algebraic, we're going to put it in this slot. The derivative of x is just dx. And because t is trig and it's to the right of a, we're going to put it in the dv slot. Keep in mind that we do have to take an integral of this, and this is where it gets even trickier because the integral of sine is that negative cosine. But you do have to account for this 2x. So it's not just negative cosine of 2x, it's actually going to be negative 1/2 of cosine of 2x. This is what I call skipping an easy u sub. If you wanted to, you could u sub this one like this. You could let the u be 2x, the derivative would have 2, and then you would bring over the 2, just like in this case right here. But if the inside function is just the line, in my opinion, it's easier just to skip the u sub. So instead of multiplying by the derivative of the inside like we do with chain rule, because we're taking antiderivatives, we multiply by the reciprocal of the derivative. So instead of multiplying by 2, we multiply by 1/2 instead. And that's an easy u sub. I feel like most of my students have gotten comfortable enough with u subs where they can skip these easy u subs. Because if we don't, then we just have to do a lot of work on this side. So let's keep going. Let's do the formula now. So now it's u times v, so it's u times v, but I'm going to write it like negative 1/2 x times cosine of 2x. So this thing times this thing. Then again, there's a lot of minuses. There's a minus in the formula because it's uv minus the integral of v du, but there's a minus here, so it looks like it's going to be minus minus, so it's going to be plus this time. uv minus the integral of v, we're going to take out the 1/2 times du. uv minus the integral of v du. So now we're ready to do this integral. Remember, unfortunately, integration by parts is a multiple step process. You do have to do this integral separately. So in this case, it's going to be negative 1/2 x times cosine of 2x. What's the integral of cosine of 2x? This is again a u sub in your head. It's going to be sine of 2x, but it's not just sine of 2x, the integral of cosine being sine, not changing the inside function. Again, we have to account for the derivative of the inside function, but instead of multiplying by 2, which we do in derivatives, we're going to multiply by 1/2. But because there's already a 1/2 here, we're going to multiply the 1/2s together and get 1/4, and this is the final answer. So hopefully you see the difference between these two integrals was quite stark, even if they look pretty similar, and it's because we did different integral methods on them. This was a very standard u sub, not much to talk about, except that we recognize it was a u sub because the derivative of this is this guy right here, or a multiple of this guy. This is a nice integration by parts question where the trickiest part of several tricky steps was this thing right here, taking the integral of dv, that it wasn't just negative cosine of 2x, we did need to multiply by the derivative's reciprocal of the inside function times 1/2. Same thing with this, the integral of cosine of 2x wasn't just sine of 2x, it was 1/4 sine of 2x. But this was a pretty standard integration by parts method besides this little u sub in our head, still u times v minus the integral of v du, where after we took the integral of v du, we were done. We had to take that as a second question, but we still use the ate to help form the rectangle. Let's do a few more questions. Let's do another u sub versus parts example. So I'm gonna erase this. Hopefully you're having fun. I'm having fun with you as we learn to review these BC integrals. They are quite difficult. It is a very challenging lesson, especially when they're all mixed up, but that's why we're doing this. So I'm gonna do a few more. Let's do the integral of x squared times e to the x cubed dx, and then I'm gonna do the integral of just x squared e to the x. So again, two integrals that look very, very similar, but they're done very, very differently. Pause the video for 5 seconds. 5, 4, 3, 2, 1. Let's go. So in this case, this is going to be my u sub because this u's derivative is in the question, a multiple of the something in the question, because the derivative of x cubed is 3x squared. Here's a little x squared. So let's u sub this real quick. It's going to be very similar to the previous ones. This is going to be u is equal to x cubed, du is equal to 3x squared. New integral time. So we chose the u so that we could put e to the u here. Then we have an x squared in dx. Well, x squared dx is right here. We're going to isolate this, so that's why there's going to be a 1/3 in the front, because x squared times dx is du over 3, and we'd like to take out the constant. It's going to be times du. This is the best integral in the world, because the antiderivative of e is just e, so it's going to be e to the u plus c. And we're going to remember to plug this in. 1/3 e, not 1/2, but 1/3 e to the x cubed plus c. Remember, you can always check your work if you want to take the derivative of this guy and see if you get back the original. Well, what's the derivative of 1/3 e to the x cubed? Well, it's 1/3 e to the x cubed times the derivative of x cubed, which is 3x squared. Those 3's will cancel, and lo and behold, you will get back the original. Let's do this a lot harder question. So again, why is this not the same process? Well, the derivative of x is not x squared, and that's really why it's not going to be the question. You might think perhaps that u is equal to x squared because the derivative of x squared is x, but if you did that u substitution, the du would be in the exponent of e, and that never happens. So that's not going to be how it's going to work. Let's do integration by parts. So in this case, x squared is considered algebraic, of course. E to the x is considered exponential. It's called e to the x for a reason. So let's write u, du, v, and dv. So it looks like it's going to be u is going to be x squared because it's algebraic with the liata, L-I-A-T-A, a is to the left of e. It means dx is going to be, dv is going to be e to the x times dx. We're going to take a derivative here, so it's going to be 2x. We're going to take an integral here, easiest integral in the world, just e to the x. And now we're doing the formula. It's u times v, so it's x squared times e to the x minus, in this case there's no other minuses, so it's just the true formula, u times v minus the integral of v du. So it would be e to the x times 2x. This should have a dx, of course. E to the x times dx. I do have a 2, so I like to take it out of my integral, and it looks like we have to do it again. Again, every single time you do integration by parts, it's u times v minus a second integral. The integral should be simpler, and in this case it is. We went from x squared to x. But just treat this second integral as a second question. You might have to do various ways to do this second integral. In the previous one, we skipped the u sub. And the one before that, I think with the ln's, we simplified it a little bit. You just have to do this integral separately, and you probably need to simplify or do an integration method in order to do it. And in this case, unfortunately, we have to do integration by parts again. But it's not going to be the worst integration by parts. So again, I'm treating this number by itself, the integral of x times e to the x dx, which is this guy right here. I'm going to do a second integration by parts. It's going to be very, very similar because a is going to be x, e to the x is exponential. We're going to have v and we're going to have dv. So what's the integral of u? What is u, what is dv? That's the real question. So what's the u? Well, it's going to be the algebraic term, and its derivative is very easy, so we might as well take that derivative. Then e to the x is going to be the dv term. Then we have e to the x here. So that's it. So then what we're going to do is we're going to do our uv minus the integral of v du, just like normal. So it's going to be x times e to the x minus the integral of v times du, which is e to the x times dx. Again, integration by parts never gives you the answer. I wish it did. That would make life so much easier. But unfortunately, it just gives you a second easier integral. You do have to do the second easier integral, but this one is not that bad. It's just going to be x times e to the x. Notice that every single time the integration by parts sort of makes the variable go down by 1, x squared to x, x to the 0, which is 1. So now, because we don't have any pesky x's, this antiderivative is a memorized antiderivative. There's no more x's, there's no more u subs that are needed to be done, there's no more integration by parts. What's the integral of e to the x? Well, it's just e to the x, of course. So what we're going to do at the very end, remember that this weird thing was just an intermediate step. This was just the answer to this integral right here. So we're going to take our hands and we're going to replace the integral and we're going to sub it in for this thing. So it's going to be equal to x squared times e to the x. We're going to have a 2, and then we're going to replace this right here with parentheses to be a little bit safe. And we're going to write plus c, and this is going to be our answer. If you want, you can distribute the 2, but I'm not really feeling it. So, pretty standard double integration by parts question. Again, just do the integration by parts method and you should be good as long as you're very, very careful as you do each successive step. And keeping in mind that you're using Liate to determine u's and dv's. When you get to that second integral, unfortunately, you might have to do integration by parts question. So just cover up all your work, write the integral down, and just think about what's the best way to do this integral, this second integral. It could be simplifying, which will make things nice. It could just be an easy u sub or a u sub in general, or it could be another integration by parts. So you have to do that integration by parts. Well, that's going to be it for all the integrals that are just given outright. Let's do some easier questions, which is when you have a table and you have f's and g's. I call these general u subs or general integration by parts, and you'll see that these questions are easier because you don't have to work with numbers, or the numbers are readily available in the table. So let's finish with this table right here and ask 2 questions. This has been a long video, of course, but hopefully I've provided enough review for you so that you are successful when you're taking BC integrals. So in this case, I'm going to draw my table here. So let's just draw a nice table. So we're going to have 2 in the table, 4 in the table, and 8 in the table. Then we're going to have f's, f primes, g and g primes. So oftentimes these are the way that they like to ask it on the free response question with these nice tables. We're going to populate these tables with random numbers, 3, -1, 6, and 5. Then we're going to choose, again, these are just random numbers. Let's choose 1 here. Let's choose 9. Let's choose -7. We haven't had a 2 yet. We haven't had a -4 yet. Let's do a +4, and we'll do, last one, we'll do a 3. So this is going to be my table. There's also going to be another given that will help us do an integral in the future from now, maybe in like 3 minutes. It's going to be that the integral from 2 to 4 of g of x times f prime of x is going to be equal to 7. So now what we're going to do, let's not change it. Let's not write 7. Let's use 12 or something. So then we're going to do these 2 integrals. It's going to be the integral of 2 to 4 of 3f double prime of 2x minus 4x. We're going to do that integral, and then after that, hopefully we'll have enough space, because I often run out of space, but we're going to do the integral of 2 to 4 of g of x prime times f of x. So we're going to do these 2 questions. Again, for the very last time, pause your video, try these integrals for yourself. These might be the most important integrals of the video, because these integrals could be ones that you might see on the AP exam, because they like to write these in sort of these big tables on the free response questions, so you don't have to know unit circle stuff or anything like that. So try these questions. I'm going to watch you as you work. Let's try them out. So in this case, theoretically, this is a u sub because there's an inside function, but again, I like to skip my easy u sub. So what's the antiderivative of this? I feel like we're confident enough just to go for the antiderivative. Well, what's the antiderivative of f double prime? Well, it's just going to be f prime. There was already a 3 in the front, and then we have 2x, but this is not the antiderivative. We do have to account for the derivative of the inside function. That's going to be 2, but instead of multiplying by 2, like with the chain rule, we're going to multiply by 1/2. So in this case, the antiderivative is 3/2. Nothing too crazy there. Then the antiderivative of minus 4x is minus 2x squared. using the power rule. Adding 1, 2, and then dividing by your new exponent, 4 divided by 2 is 2. Then we're going to plug in x's equal to 2 and 4. So hopefully you see that work wasn't too bad. You could use sub this, you could write u is equal to 2x, you could write du is equal to 2 times dx, you could have a second integral 3f double prime of u times du, taking out the 2, and then changing your numbers to 4 and 8, and taking this integral. But again, I think it's easier to skip these easy u subs because it's just basically the chain rule, but instead of multiplying by the derivative, you multiply by the reciprocal of the derivative. But again, these questions are going to be easier because you are going to use a table. It is top minus bottom still, so let's try this. What we do is we're going to plug in 4. So when we plug in 4, it looks like it's going to be 3 halves times f prime of 4 times 2, actually. So we're going to plug in 4. 4 times 2 is 8, so it's f prime of 8. So it looks like it's going to be negative 7. Not my favorite number in the world, but whatever. Then we plug in 4. This one's a little bit nicer because there's no fractions. 4 squared is 16. 16 times 2 is 32. Then we're going to plug in 2 into this, so it's going to be 3 halves again. And when we plug in 2, it's going to be f prime of 4, but f prime of 4 is 9. Finally, we're going to plug in 2, still top minus bottom. Notice how careful I am being with parentheses, as I normally am. So when I plug in 2 here, notice it'll be 2, 4, 8. 2 squared times 4, so it's going to be 8. So now all we have to do is a little bit of fraction work, which is not my best friend, but I think I'm going to be able to do it. It's going to be negative 1 minus 27. 21 plus 27 is 48, so that's going to be divided by 2. So it's going to be negative 24. Then let's write this terribly vertically. So then it's going to be minus 32, because we have this minus 32. And then finally it's minus 8, so it's plus 8. So what is this going to be? Well, minus 24 minus 32. Let's not do any math crazily. Well, minus 32 plus 8, that's minus 24. So minus 24 minus 24. I believe that the answer is minus 48. Might not be true, but hopefully that is correct. We can sort of box our work here. But keep in mind that this integral, again, wasn't too bad. You just had to account for this has, basically, if you do know the power rule. Skip those easy u subs if you can. This one also isn't too bad. What we're going to do is we're going to do the normal integration by parts method. So it's going to be u, du, v, and dv. Unfortunately, we cannot use Liate because Liate doesn't have f and g's. It only accounts for functions that are explicitly given, like ln's and exponentials. So we do have to determine one. One of these, g prime, and one of these of f will go in the u spot, and the other will go in the dv spot. But it should be pretty easy. For example, if you let the u be g prime, well, you're going to take its derivative, and that's going to be g double prime, but there's no g double primes in any of the givens, so that's probably wrong. So g prime is going to be in this slot right here, and then u is going to be the rest of it, f of x. So what we're going to do is we're going to take a derivative, f prime of x dx, but that's probably good because look at this. Then the integral of g prime is, of course, g of x. So now we're ready for the answer. So this integral right here, I'm going to write right here. So hopefully you can see that this is a box. But I'm taking this integral and I'm just going to employ the formula. Let's not look at any of the givens. So it's u times b, f of x, times g of x. We're going to plug in 2 and 4. Then we're going to subtract and then take the integral of v du, just like normal, even if you have f's and g's. So it's going to be the integral of 2 to 4. G of x times f prime of x. Again, just like we've been stressing for every single integration by parts question throughout the video, integration by parts doesn't give you the answer. It hopefully gives you a simpler integral. So I do have to know what this integral is here. It looks like I don't know what it is because how in the world am I going to find the integral of g times f prime? But that's why it was given. And that's why these questions are usually a lot easier. In the previous question, what we did is we had to do a second integration by parts. But in this case, all we have to do is take this integral and replace it with 12. So in this case, it's going to be minus 12. Nothing too crazy. But again, you do have to account for that second integral. You can't just go straight to the answer. Finally, it's going to be f of 4 times g of 4 minus f of 2 times g of 2. And it looks like we just have a little bit more math. So what's going to be the answer here? I think we have enough space to put it right here on the bottom of this little board. Well, what's f of 4? Reading the table one more time, it's going to be 5 times g of 4, which is 2. 5 times 2. Then it's going to be f of 2 times g of 2, so 3 times 6. Finally, minus this 12. It's going to be 10 minus 18 minus 12. Well, 18 plus 12 is 30, so 10 minus 30 is negative 20. So hopefully you see that these integrals that are given in these tables are usually easier, and the good news is that they're more commonly asked, especially with integration by parts. But again, it's the same thing. Choose your u and du, dv, v, not based off of Liate, but which one makes the most sense. Which one do I want to take the integral of? Basically, which one do I want to take the derivative of? Didn't make sense to take the derivative of g prime because it's not in the table. Also, I have no idea what the antiderivative of f is, so it cannot be in this slot. We do our normal process. U times v minus the integral of v du. This integral, again, we have to do, but in this case, it was very easy. We just replaced it with the number 12 because that was a given. And then finally, fundamental theorem of calculus, one more time, plugged in 4, minus plugged in 2, and then finally found the answer. So this has been one of our longest videos ever, but that's because integration by parts and integration by partial fractions and u-subs and improper integrals is just a very difficult topic. So what we would recommend is for you to go back, watch our previous videos where we talked about some of the questions that we weren't even able to cover in this super long video. So there were a few BC integrals that weren't covered in this video. For example, really hard u-subs like cosine of square root of x over square root of x, absolute value questions, the famous add back, e to the x times cosine of x, and integration by parts. So go back to throughout this playlist as needed to check out some other examples for more practice. Like usual, we do have a Girls Teach Calculus video in the link of the description of this video if you want to practice more integrals. She does some where the integrals are partial fractions, parts, using a table, u-subs, anything like that, maybe even some fundamental theorem of calculus questions. That girl was a former student of mine and she explains things very, very well, so we highly recommend you watch this. This has been a very long video. I did enjoy my time with you as we went through these BC integrals. Hopefully this was a big help for you. This is why we like to do this. Give us a like, subscribe if this was a big help for you. And this does conclude our integration method video, but hopefully whatever video I see you next in, I will enjoy that time and you will enjoy that time. But for now, thanks again for watching and goodbye.